In 1977, humanity launched 2 spacecraft, but are, as of this moment, the farthest human-made objects from Earth. Voyager 1 and Voyager 2, now travelling at roughly 17 and 15 kilometers per second respectively, have crossed what scientists call the heliopause, the boundary where the sun's solar wind gives way to interstellar space. We celebrate this as a triumph of engineering and ambition, and it is. Voyager 1 is approximately 23 billion kilometers from Earth. It took 46 years to get there. The nearest star to our Sun, Proxima Centauri, a dim red dwarf 4.24 light-years away, is approximately 40 trillion kilometers from Earth. At Voyager 1's current speed, it would take roughly 73,000 years to reach it. Not 73,000 days, not 73,000 months, 73,000 years. Longer than the gap separating us from the Neanderthals, longer than the entire span of anatomically modern human civilization. And Voyager is not even heading in the direction of Proxima Centauri. If it were, 73,000 years from now, it would arrive at the nearest star, not at a habitable world, not at a civilization, not at anything of particular interest, having crossed 4.24 light-years out of the Milky Way's 1,000 light-year diameter. It would have covered 0.4% of the galaxy. If you enjoy videos that take the hardest questions in space science and work through them with full honesty, that never let ambition substitute for precision, that take seriously both the wonder and the limits, I genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. The most common misconception about interstellar travel is that it is simply a matter of engineering, that given enough time, enough money, enough ingenuity, humanity will eventually build the ships that cross the stars. Because that is what humanity does. We solved powered flight. We reached the moon. We built the internet. We will solve this too. It is just the next problem. This framing is wrong in a way that is not merely pessimistic, but physically precise. Interstellar travel is not hard the way that building the first airplane was hard, a problem of sufficient cleverness applied to tractable engineering. It is hard the way that perpetual motion is hard. There are physical laws that constrain the problem so severely that no amount of engineering cleverness addresses the fundamental obstacles. The rocket equation is merciless. The speed of light is an absolute limit. The energy required for fast interstellar travel is not merely large, it exceeds the total energy output of any energy source that does not require physics we do not have. The distances are not merely great, they are great in units of the speed of light, which is the fundamental currency of information and causation in the universe. None of these obstacles is a question of will or resource. They are questions of physics. And the physics, examined honestly, raises the genuine possibility that interstellar travel, not just currently difficult interstellar travel, but any interstellar travel by biological creatures on timescales that matter to civilization, may be permanently beyond what this universe permits. That is the argument this video will make. Not with certainty, intellectual honesty requires acknowledging what we do not know, but with the rigor that the subject demands. We will work through the obstacles one by one, the energy problem, the time problem, the engineering problem, the biological problem, the navigation problem, the deceleration problem, the communication problem, and finally, the most underappreciated obstacle of all, the motivation problem. And at the end, having worked through all of them, we will ask what the honest conclusion is and what it means for our understanding of our place in the universe. Begin with the most fundamental obstacle, energy, because every other problem in interstellar travel is downstream of energy, and the energy numbers, calculated carefully, are not merely large, they are civilization-ending large. But to understand why the energy numbers are so large, we first need to understand exactly why chemical rockets, the technology we have actually mastered, are so thoroughly inadequate for interstellar travel. Not insufficient, not underpowered. Inadequate in a categorical sense, chemically propelled interstellar travel is ruled out by the same mathematics that rules out perpetual motion. The rocket equation, derived by Konstantin Tsiolkovsky in 1973, governs the relationship between a rocket's exhaust velocity, its mass ratio, and its final change in speed. It is one of the most merciless equations in engineering. The final velocity of a rocket equals the exhaust velocity multiplied by the natural logarithm of the mass ratio, the ratio of the starting mass fuel plus spacecraft to the ending mass spacecraft only. For chemical rockets, the exhaust velocity is set by the chemistry. Hydrogen-oxygen combustion, the most energetic chemical reaction used in propulsion, produces an exhaust velocity of about 4.4 kilometers per second. The natural logarithm function grows slowly. To get a final velocity of 10 exhaust velocities, you need a mass ratio of e to the power of 10, which is about 22,000. To get 20 exhaust velocities, you need e to the power of 2, which is about 485 million. The exponential in the denominator makes the rocket equation not just a quantitative obstacle, but a qualitative one. The fuel required to reach high multiples of the exhaust velocity grows faster than any conceivable source of propellant. The escape velocity from the solar system, the speed needed to leave the sun's gravity from Earth's orbit, is about 42 kilometers per second. That is about 9.5 times the exhaust velocity of the best chemical rocket. A chemical rocket must therefore have a mass ratio of e to the power of 9.5, about 13,000. For every kilogram of payload, 13,000 kilograms of fuel. And that does not include the structural mass of the fuel tanks, plumbing, engines, and everything else needed to hold all that fuel. To reach 1% of the speed of light, 3,000 kilometers per second, using chemical propulsion with a hydrogen-oxygen exhaust velocity of 4.4 kilometers per second, the required velocity is about 682 times the exhaust velocity, and the mass ratio is e to 682,000, which is approximately 10 to the power of 296. That is a number so large it exceeds the number of atoms in the observable universe by a factor of 10 to the power of 200. There is not enough matter in the observable universe to fuel a chemically propelled spacecraft to 1% of the speed of light. This is not a problem of engineering or resources. It is a fundamental incompatibility between the energy density of chemical reactions and the kinetic energy required for interstellar travel. The nearest star system to our own is Alpha Centauri, a triple system consisting of Alpha Centauri A, a star slightly larger and brighter than our Sun, Alpha Centauri B, slightly smaller and dimmer, and Proxima Centauri, the red dwarf companion, at 4.24 light-years. If humanity decided tomorrow to send a crewed spacecraft to this nearest possible destination, not across the galaxy, not to some exotic target, but to the closest stellar system that exists, what would it take energetically? Let us work through the minimum case, a spacecraft with a total mass, including crew, life support, fuel, and everything else, of 100 tons. This is smaller than the International Space Station, which masses about 420 tons, and far smaller than any spacecraft that could realistically support a crew for the decades to centuries such a journey would take at any achievable velocity. But let us use 100 tons as a minimum illustrative figure. To reach Alpha Centauri in a reasonable time frame, let's say 100 years, which is already a multi-generational voyage, the spacecraft needs to travel at about 4.24% of the speed of light, or approximately 12,720 kilometers per second. At this speed, the kinetic energy of a 100-ton spacecraft is approximately 9.7 times 10 squared 1 joules. In more comprehensible terms, the total energy output of the entire Sun in about 25 milliseconds. Or the total energy consumption of human civilization for the next 750 years at current rates. For a 100-year voyage to the nearest star in a 100-ton spacecraft. But this calculation understates the problem in a critical way because it only accounts for the kinetic energy of the spacecraft at cruise velocity. It does not account for the energy needed to accelerate the spacecraft to that velocity, or, crucially, the energy needed to decelerate it at the destination. A spacecraft that arrives at Alpha Centauri at 4.24% of the speed of light, with no way to slow down, is not making a visit. It is making a flyby that lasts a few hours before the spacecraft recedes into interstellar space at the other side. A crewed mission requires deceleration, and deceleration, by the rocket equation, requires just as much energy as acceleration, more, in fact, because the spacecraft has to carry the deceleration fuel for the entire outbound trip, which means it has to accelerate that fuel too, which means it needs more fuel to accelerate the deceleration fuel, which means it needs more fuel for that fuel, and so on in the exponential escalation that makes the rocket equation so devastating. The Tsiolkovsky rocket equation governs all rockets. Delta V equals exhaust velocity times the natural logarithm of the mass ratio, the ratio of the initial fully fueled mass to the final empty mass. For a round trip to Alpha Centauri at 4.24% of light speed, with acceleration and deceleration at both ends, the total delta V required is roughly 4 times 12,720 kilometers per second, or about 51,000 kilometers per second. The exhaust velocity of the best propellant currently available, antimatter-matter annihilation products, approaches the speed of light, but even assuming perfect conversion and a purely photon rocket exhaust velocity equals c, the mass ratio required for a delta V of 51,000 kilometers per second is e to the power of 51,000 divided by 300,000, or e to the power of 0.17, which equals approximately 1.18. This sounds manageable, an 18% fuel fraction. But this assumes a photon rocket, a rocket that converts mass entirely into directed photons. No such technology exists, or has any near-term prospect of existing. The best real propulsion concepts, nuclear pulse, fusion, have exhaust velocities of perhaps 10,000 to 30,000 kilometers per second. With a fusion rocket at 10,000 kilometers per second exhaust velocity, the mass ratio for the same trip is e to the power of 51,000 to 10,000 kilometers per second, equals e to the power of 5.1, approximately 164 kilograms. For every kilogram of spacecraft, 163 kilograms of fusion fuel. A 100-ton spacecraft requires... Antimatter propulsion is often cited as the ultimate energy solution, and the physics supports its exceptional appeal. When matter meets antimatter, both are completely annihilated, and the entire rest mass of both is converted to energy. With an energy density of 9 times 10^116 joules per kilogram, 10 billion times the energy density of chemical fall, and about 140 times the energy density of hydrogen fusion. A photon rocket powered by antimatter annihilation would have the theoretical maximum exhaust velocity of the speed of light, and the mass ratios for interstellar missions become manageable. For a round trip to Alpha Centauri at 50% of the speed of light, using a perfect antimatter-powered photon rocket, the mass ratio is about a 9. 8 kilograms of fuel per kilogram of payload. This is the dream. The energy density of antimatter makes the rocket equation tractable for interstellar travel. The problem is the fuel. The entire production of antimatter by human civilization, by all the particle accelerators ever built over all the decades they have operated, amounts to perhaps a few nanograms total. A nanogram. 1/1000th of a gram. The Large Hadron Collider at CERN produces antiprotons at a rate of roughly 10 billionths per second, about 10 femtograms per year. At this rate, producing 1 gram of antihydrogen would take about 100 billion years, roughly 7 times the current age of the universe. The estimated cost of producing 1 gram of antimatter using current technology is in the range of tens of trillions of dollars. Storage is separately impossible. Antihydrogen must be confined in a magnetic trap and is annihilated by any contact with ordinary matter, including residual gas in the best vacuum chambers. No one has stored more than a handful of antihydrogen atoms for more than a few minutes. To power a 100-ton spacecraft on a round trip to Alpha Centauri using antimatter propulsion requires, even under optimistic assumptions, several hundred tons of antimatter. The gap between a few nanograms total ever produced and several hundred tons needed is a factor of roughly 10 squared 101. Not 10 times, 10 sextillion times more antimatter than has ever been produced by humanity, at costs that would require an economy millions of times larger than Earth's current economy. Antimatter is not a technology on the horizon. It is a theoretical limit that illustrates what perfect mass-to-energy conversion could achieve, while simultaneously illustrating how impossibly far we are from achieving it. The energy problem scales with the ambition of the mission. A faster trip, 10% of the speed of light, reaching Alpha Centauri in 42 years, requires 4 times as much kinetic energy. A 1% of light speed mission, 424 years to Alpha Centauri, requires 100th of the energy of the 10% mission, but still vastly more than any plausible near-term energy source. Every improvement in speed costs energy quadratically. Double the speed, quadruple the energy. Every improvement in trip time tightens the energy demand proportionally. There is no clever route around this. The energy is in the physics, not in the engineering. You can make a more efficient rocket, a lighter spacecraft, a better fuel, but you cannot make the kinetic energy smaller, because the kinetic energy is determined by the mass and the speed, and the mass is determined by the minimum requirements for a functional crewed mission, and the speed is determined by the maximum time the mission can take. And this brings us directly to the second great obstacle, time. The nearest star is 4.24 light-years away. This is not a distance in the ordinary sense, not a distance like the length of a river or the circumference of the Earth. A distance that human civilizations have crossed and recrossed and mapped and comprehended in the way that things comprehended by the human mind become domesticated. It is a distance measured in the time that light, the fastest thing in the universe, takes to cross it. 4 years and 3 months for light to travel from Proxima Centauri to Earth. For any spacecraft slower than light, the crossing takes longer. How much longer depends on the speed, which depends on the energy, which we have just established is staggering. At speeds achievable by any technology in serious consideration, the journey times are not 4 years and a few months. They are decades to centuries for the nearest star and thousands of years for anything interesting beyond the immediate stellar neighborhood. Let us be specific about what interesting beyond the immediate stellar neighborhood means. The Alpha Centauri system, the nearest, contains at least one confirmed exoplanet, Proxima Centauri b, a potentially rocky world orbiting in the habitable zone of Proxima Centauri. But Proxima Centauri is an active flare star that periodically blasts its nearby planets with ultraviolet and X-ray radiation, intense enough to potentially strip atmospheres and sterilize surfaces. Whether Proxima Centauri b is genuinely habitable is deeply uncertain, and even optimistic assessments place its habitability at the lower edge of plausibility. The nearest stars that might have planets with conditions genuinely conducive to life, Grams and K-type main sequence stars, with stable radiation environments, at distances compatible with liquid water, are typically 10 to 50 light-years away. Tau Ceti, at 11.9 light-years, has multiple planet candidates, including some in or near the habitable zone. Veselong Eridani, at 10.5 light-years, is a young K-type star with a debris disk suggesting planetary system activity. 40 Eastradani A, at 16.3 light-years, is an orange dwarf with at least one candidate planet. At 10% of the speed of light, Tau Ceti is a 119-year journey. At 1% of the speed of light, the kind of speed achievable by plausible near-future fusing propulsion, it is a 1,190-year journey. The nearest genuinely interesting targets are not years away. They're centuries to millennia away at any speed we can seriously contemplate. These timescales interact catastrophically with human biology. The current record holder for human spaceflight duration is approximately 437 days in space by cosmonaut Valery Polyakov on the Mir space station in 1994 to 1995, and about 371 days on the ISS by several NASA and Roscosmos astronauts in recent years. The medical consequences of even these comparatively short durations in microgravity are significant and well documented. Bone mineral density declines at a rate of roughly 1 to 2% per month in microgravity, even with vigorous daily exercise. After 6 months in space, astronauts have lost bone density equivalent to a decade of aging, and while much of it recovers after return to gravity, the recovery is incomplete and takes months to years. Muscle mass declines even more rapidly, without the constant effort of carrying one's own weight against gravity. The cardiovascular system adapts to the lower circulatory demands of microgravity by reducing blood volume and cardiac output, which requires readaptation upon return to gravity. Vision problems caused by increased intracranial pressure in microgravity, which deforms the eyeball and the optic nerve, have been found in a significant fraction of astronauts after long-duration missions. The brain itself shows measurable structural changes, redistribution of white matter, slight increases in cerebrospinal fluid volume that researchers are still working to understand. All of these effects are for missions of months. For a mission of decades, a 40-year journey to Alpha Centauri at 10% of light speed, the cumulative biological damage is unknown, but expected to be severe. Some of it could be mitigated by artificial gravity, spinning sections of the spacecraft to create centrifugal acceleration. But spinning a spacecraft large enough to support a crew produces its own engineering challenges. The structural loads of rotation, the gyroscopic effects on navigation, the Coriolis effects that disrupt human balance and coordination at low rotation rates. It is a solvable problem in principle, but it adds mass and complexity to a system that already has too much of both. Radiation is separately devastating. On the ISS, astronauts receive radiation doses of roughly 80 millisieverts per year, about 40 times the dose received on Earth's surface, but still within the range where statistical cancer risk increase is modest. In deep space, beyond Earth's magnetic field, the galactic cosmic ray flux is roughly twice the ISS dose, and solar particle events can add large acute doses on top of the background. On a journey of decades in deep space, the cumulative radiation dose would significantly exceed the career limits that NASA and other space agencies currently impose on astronauts. "Hello there," asked back. The long-term cancer risk, the risk of radiation-induced cataracts, the potential for central nervous system effects from heavy cosmic ray ions. These are not managed by existing technology. Shielding against cosmic rays requires very large amounts of material, hundreds of grams per square centimetre of water-equivalent shielding to reduce the dose to anything approaching acceptable, and the mass penalty is enormous. My caveat: for a 40-year journey, adequate shielding against cosmic rays would add thousands to tens of thousands of tons to the spacecraft mass, multiplying the energy requirements by corresponding factors. A 1,000-year journey requires a generation ship. A 1,000-star journey, the kind required to reach interesting stellar targets at currently imaginable speeds, requires dozens of generations. A 10,000-year journey, which is what Voyager's speed implies for the nearest star, requires something more than a generation ship. It requires a civilization in a can, a society, a culture, a history, a politics, all contained within a spacecraft, evolving over timescales longer than the gap from the first cities to the present day. The people who eventually arrive, if anyone survives, and the mission goal is even remembered, have no meaningful connection to the civilization that launched them. They are not ambassadors of Earth. They are a separate species in formation. These problems were understood well before the space age. The biologist J.B.S. Haldane noted in the 1920s that interstellar travel would require either immortality, which we do not have, or the willingness to condemn future generations to a journey they did not choose, which raises profound ethical questions. The fact that these questions have not been resolved in a century of science fiction engagement with the concept is not because they are difficult technical problems waiting for clever solutions. It is because they are not technical problems. They are philosophical problems about what it means to make choices for people who do not yet exist, and they resist technical solutions because they are not technical in nature. Consider the analogy of colonization voyages in human history, which some use to argue that generation ships are simply the next version of the Mayflower or the Polynesian voyages of discovery. The analogy is instructive, but ultimately fails in the critical dimension. The Polynesian navigators who set out from Southeast Asia and eventually reached Hawaii and New Zealand were making voyages of months to years, not decades or centuries. They were still in contact with the sky they had always known, navigating by stars they had learned from childhood, arriving at islands that were at least superficially similar to the islands they had left. The crew of a generation ship is in a fundamentally different situation. They are enclosed in an artificial environment with no natural reference to any external world, for a journey measured in generations, heading toward a destination that may be entirely unlike anything Earth's biology is adapted to. The Polynesian Voyager reached the other shore within their own lifetime, adjusted and built a new life. The third generation of a generation ship crew has never seen a sky, has never stood under an open horizon, has never experienced weather or seasons, or the passage of night and day in the form that human cognition evolved to process. They are adapted to a spacecraft, and the destination, however wonderful, is as alien to them as the spacecraft was to the people who launched it. The ethics of generation ships have been explored by philosophers and legal scholars who point out that the crew beyond the first generation did not consent to the voyage, cannot leave, cannot change their circumstances, and are committed by the choices of their ancestors to a project and a destination they had no part in choosing. This is not a minor ethical concern that can be set aside in the excitement of exploration. It is a fundamental question about the rights of people who did not yet exist when the decision was made, and it has no clean resolution. There is one proposed alternative that sidesteps the generation ship problem for biological humans: suspended animation or cryogenic preservation. Place the crew in biological stasis at the beginning of the journey and revive them at the destination. No generational succession, no ethical problem of non-consenting future crew. But suspended animation for mammals over periods of decades is not currently possible and may not be biologically achievable. The longest mammalian hibernation known is about 8 months for certain ground squirrels. Extending this to decades would require either an entirely different mechanism of metabolic suppression, one that prevents the normal biochemical degradation of proteins, lipids, and DNA that occurs during extended quiescence, or a physical preservation technique like cryonics, which involves cooling the body to liquid nitrogen temperatures and storing it in ice. Cryonics is advocated by some as a way to preserve people who have died, but no mammal has ever been cryonically preserved and successfully revived. The ice crystal damage to cell membranes during freezing and the unknown effects of the revival process remain unresolved. For a journey of decades, suspended animation is not a mature technology, but a hope, and the distinction matters. Unless, of course, the journey can be made fast enough that the travellers are still alive at the destination. If the archaeologists had that strategy, which brings us back to speed, and to the third major obstacle, the engineering of high-speed interstellar travel, which is where the challenges multiply in ways that no single clever insight resolves. To reach Alpha Centauri in a single human lifetime, say 40 years, which is already a significant portion of a working career, requires a speed of roughly 10% of the speed of light. This is a velocity at which the engineering problems become not just difficult, but qualitatively different from anything in human experience. At 10% of the speed of light, the spacecraft is travelling at 30,000 kilometers per second. In 1 second, the spacecraft moves 30,000 kilometers. The diameter of Earth is 12,742 kilometers. The spacecraft crosses the Earth's diameter in 0.42 seconds. It crosses the distance from Earth to the Moon in 12.8 seconds. In 1 minute, it travels 1.8 million kilometers, farther than the diameter of the Sun. At this speed, the interstellar medium, the gas and dust that fills the spaces between stars, is not empty space that can be ignored. It is a radiation hazard of the first order. The interstellar medium contains, on average, about 1 hydrogen atom per cubic centimetre. This density is extraordinarily low, far lower than the best vacuum achievable in a laboratory on Earth. But at 10% of the speed of light, each hydrogen atom the spacecraft encounters has a kinetic energy in the spacecraft's reference frame of approximately 4.7 million electron volts. That is the energy of a medium-energy cosmic ray proton. The spacecraft, at this speed, is continuously bombarded by what are, in its reference frame, cosmic ray particles. The forward-facing surface of a spacecraft receives a particle flux equivalent to a continuous dose of hard radiation. Over a 40-year journey, the cumulative radiation dose on any unshielded surface would be extraordinary, sufficient to destroy most materials, to kill any unshielded crew repeatedly over, and to induce nuclear reactions in any shielded material sufficiently thick to stop the particles. The shielding problem is not simple. To stop a 4.7 million electron volt proton, you need several centimeters of dense material: lead, water, polyethylene. But the spacecraft, at this speed, encounters not just hydrogen protons, but heavier interstellar ions, and not just the diffuse interstellar medium, but interstellar dust grains. A single interstellar dust grain, a micron-sized particle of silicate or carbon, with a mass of perhaps 10⁻115 kilograms, at 10% of the speed of light, carries a kinetic energy of about 450 joules. For comparison, a rifle bullet carries about 3,500 joules of kinetic energy. The spacecraft, at this speed, is struck by the equivalent of a sub-rifle bullet with every dust grain it encounters. The rate of such encounters, integrated over the journey, is not negligible. The interstellar medium has a dust density of roughly 1 grain per million cubic meters, and the spacecraft sweeps through a cross-sectional area of perhaps 100 square meters. Over a 40-year journey, at 10% of light speed, the spacecraft encounters tens of millions of dust grains, each delivering 450 joules of kinetic energy to the forward surface. The total energy deposited by dust impacts alone is on the order of 10,010 joules. Concentrated in the forward shield, this is equivalent to several tons of TNT delivered in small but continuous bursts over 40 years. No material currently known to us can withstand this assault over a 40-year journey without catastrophic erosion. The leading edge of any forward shield would be ground away by continuous impact, requiring either an enormous initial thickness or a replenishment system. The engineering of a material that can absorb 450 joules impacts at millions per year while maintaining structural integrity is not a solved problem in materials science. It is not even close to a solved problem. And this is at 10% of the speed of light, not 50%, not 99%, but 10%. The problem scales with velocity squared. At 50% of light speed, each dust grain carries 25 times more energy. There are proposed mitigations. One is a magnetic deflection system, a powerful magnetic field projected ahead of the spacecraft that would ionize dust grains and deflect the resulting plasma around the spacecraft. This works for electrically charged particles, but not for neutral particles, or for dust grains that are too large to fully ionize. Another is a physical shield, a large, expendable mass of material at the front of the spacecraft that absorbs the dust and radiation impacts, progressively eroding while protecting the main structure. A third is active avoidance, a system that detects obstacles ahead and steers around them. None of these is technically mature. None has been tested even in principle at the relevant scales and velocities. And all of them add mass, complexity, and energy requirements to the mission, which feeds back into the propulsion problem. The navigation problem is separate from the interstellar medium problem, but equally challenging. Space between stars is not empty and uniform. The trajectory from our solar system to Alpha Centauri passes through regions of varying gas and dust density, varying magnetic field strength, and unpredictable gravitational perturbations from other nearby stars. A spacecraft travelling at 10% of the speed of light cannot make significant course corrections. At this speed, the reaction mass required to change course by even a small angle is prohibitive. The trajectory must be planned with extraordinary precision before departure, and it must be trusted for the entire duration of the journey. Any error in the initial trajectory that places the spacecraft on a path passing through a denser than expected dust cloud, or aimed slightly wrong at the destination, cannot be corrected mid-journey without consuming propellant that is needed for deceleration. The precision of navigation required for an interstellar mission, without the ability to make significant mid-course corrections, demands a knowledge of the interstellar environment between here and the destination that we do not currently have and cannot obtain without sending reconnaissance probes first, which takes decades to centuries, at any speed we can currently achieve. The communication problem is profound in a different way. At 4.24 light-years from Earth, a radio message takes 4.24 years to arrive. Any instruction sent from Earth in response to a situation the spacecraft reports arrives at the spacecraft 8.48 years after the situation was first reported. The crew cannot receive real-time guidance. They cannot consult with Earth's engineers or physicians or commanders. They are, for all practical purposes, entirely alone, not just physically isolated, but informationally isolated, in a way that no human crew has ever been. The Apollo astronauts, at the Moon, were 1.3 light seconds from Earth. The Mars surface at average distance is 12.5 light minutes. These are manageable communication delays. 4.24 light years is a different category entirely. The crew of an interstellar mission cannot expect help from Earth. They are the entire human civilization for the duration of their voyage, in terms of any decision that needs to be made faster than a decade. This isolation, informational, physical, psychological, is not just a quality of life problem. It is a systemic risk problem. Any equipment failure that the crew cannot repair with onboard resources and knowledge will be fatal. Any medical emergency that requires expertise not represented in the crew will be fatal. Any conflict or psychological breakdown in the crew will be addressed without external mediation. The crew must be entirely self-sufficient, not for a day or a week or a year, but for the entire duration of the voyage, which may be decades or centuries. The redundancy required in every system, the breadth of expertise required in every crew member, the psychological resilience required in people who are permanently cut off from the civilization that produced them. These requirements are not impossible in principle, but they have never been achieved in practice. And the smaller the crew, the harder each requirement is to meet. Now let us address what may be the most technically demanding single problem in the entire enterprise: deceleration. It is a problem that is often glossed over in discussions of interstellar travel, and the glossing over makes the whole enterprise seem more tractable than it is. A spacecraft accelerates to some fraction of the speed of light. Then, for the middle portion of the journey, it coasts, engines off, travelling at constant speed through the void. Then, approaching the destination, it needs to slow down. If it does not slow down, it arrives at the destination in a matter of hours at high speed and then recedes into interstellar space in the other direction. For a crewed mission, deceleration is not optional. But deceleration requires propellant, and that propellant must have been carried for the entire journey, or must be somehow gathered en route. Carrying the deceleration propellant from the start is the worst option from an energy perspective, because the rocket equation applies. The spacecraft must carry enough fuel to decelerate not just itself, but all the deceleration fuel that will be needed. If deceleration requires the same fuel fraction as acceleration, which it roughly does, the total fuel fraction is not double what acceleration alone requires. It is the square, because the spacecraft must accelerate the deceleration fuel. This exponential blow-up is the reason that even the most technically advanced propulsion concepts, nuclear pulse, fusion, produce mass ratios that are impractically large for round trips. The mass ratio for a round trip to Alpha Centauri at 10% of light speed using fusion propulsion with a 10,000 kHz exhaust velocity is approximately e to the power of 120,000 divided by 10,000 equals e to the power of 12, approximately 162,754. For every kilogram of crew, life support, and spacecraft, roughly 162,753 kilograms of fusion fuel. A 10-ton spacecraft requires 1.6 million tons of fusion fuel. There is no plausible way to acquire and store 1.6 million tons of fusion fuel for a single mission. The alternatives: gathering fuel en route, using a magnetic scoop to collect interstellar hydrogen for fusion, the Bussard-Ramjet concept, face their own severe obstacles. The Bussard-Ramjet's fundamental problem, as discussed in previous videos and confirmed in detailed analyses, is that the drag from the magnetic scoop on the interstellar medium exceeds the thrust from the fusion reaction, particularly for the proton-proton fusion reaction that is the only one available from interstellar hydrogen. The ramjet may decelerate you more than it accelerates you. Modifications: the catalytic ramjet, the laser-boosted ramjet, various hybrid concepts address some of these issues, but not all, and none has been demonstrated in principle at any relevant scale. Beamed propulsion, using a powerful laser or particle beam from the solar system to accelerate a light sail or probe, solves the propellant problem for acceleration, but not for deceleration. The beam cannot follow the spacecraft to the destination. At interstellar distances, even the most tightly focused laser beam spreads to a size far exceeding any plausible sail. The breakthrough Starshot proposal, for example, involves accelerating a ground-scale sail to 20% of the speed of light using a ground-based laser array, but it explicitly does not address deceleration, because deceleration at the deceleration is not possible for this concept without additional infrastructure. The sail arrives at Alpha Centauri at 20% of the speed of light and cannot stop. It transmits data during the few-hour flyby and then recedes. For a probe, this is acceptable. For a crewed mission, it is not. Proposed solutions to the deceleration problem at the destination: deploying a magnetic sail that brakes against the stellar wind of the destination star, using the destination star's light to brake a reflective sail, using a pre-placed infrastructure to receive and decelerate the spacecraft. All require either that significant equipment be sent ahead of the crewed mission, requiring the same propulsion problems to be solved in advance for the scouting mission, or that some clever physics trick allows the spacecraft to extract kinetic energy from its environment. None of these is currently more than a theoretical sketch. None has been demonstrated even at model scale. Each one, examined in detail, reveals its own sub-problems that are each individually comparable in difficulty to the overall problem. Having worked through the energy, time, engineering, navigation, communication, and deceleration problems, we arrive at what I called earlier the most underappreciated obstacle of all, the motivation problem, which is not a physics problem, not an engineering problem, not a biology problem. It is a civilization problem, and it may be the most practically limiting of all, because all the others might theoretically be solved given sufficient civilization scale motivation. And the question is whether such motivation can ever be sustained. Consider what would be required. An interstellar mission that reaches Alpha Centauri in 40 years at 10% of the speed of light requires, conservatively, an energy budget equivalent to hundreds of years of current human civilization's total energy production. It requires a propulsion technology, fusion or antimatter, but does not currently exist and whose development would itself be a decades to centuries long project. It requires spacecraft engineering at scales and performance levels that are orders of magnitude beyond anything currently built. It requires selection and training and psychological preparation of a crew for a journey that has never been made to a destination that may hold nothing of practical value to the civilization funding the mission. And it requires a funding commitment that spans generations, from the decision to build, through the construction phase, through the 40-year journey, to the arrival and the 4.24-year communication delay before Earth receives any confirmation that the mission succeeded. The total elapsed time from civilization decides to attempt interstellar travel to civilization receives the first signal from the arriving crew is, optimistically, 60 to 100 years, depending on how long development and construction take. More realistically, given the technological gaps between current capability and what is required, it is 200 to 500 years. No democratic government, no corporation, no institution that exists today will be the same institution 200 years from now. No funding commitment made today will still be honoured in 200 years. No political coalition that could authorise such a project will be in power for long enough to complete it. The decision-making horizon of human institutions, governments, companies, international treaties, is measured in years to decades, not centuries. Democracies operate on electoral cycles of 2 to 6 years. Corporations optimize for quarterly earnings and multi-year strategic plans. Even the most ambitious multi-decade programs, the International Space Station, which required 30 years from first serious concept to completion, the James Webb Space Telescope, which took 26 years from initial concept to launch, barely achieved 2-decade institutional persistence. An interstellar travel enterprise requires century-scale institutional commitment to a project that offers no economic return, no security benefit, no political constituency, and no tangible result for the first 60 to 100 years of the commitment. This is not an argument that human civilization is too short-sighted or too self-interested, though sometimes it is both. It is an argument about the structural properties of human institutions. Even the most ambitious long-term human projects, the great cathedrals of medieval Europe, which were built over centuries, the Roman road network, the Great Wall, were built by institutions that were continuously motivated by concrete, near-term benefits, religious prestige, military control, border security. An interstellar mission offers no such near-term benefits. The motivation must be purely exploratory and sustained across generations, and a civilization that is simultaneously managing all the ordinary crises and opportunities that make the near term always more pressing than the very long term. Consider the history of ambitious scientific mega-projects as a test case for what institutional persistence actually looks like in practice. The superconducting supercollider, the most ambitious particle accelerator ever proposed in the United States, was authorized by the US Congress in 1987, began construction in Texas, and was cancelled by Congress in 1993, 6 years after authorization and after $2 billion had been spent, because the political winds had changed and the budget pressures of the moment outweighed the scientific case that had seemed compelling a few years earlier. The SSC was a $12 billion project, a relatively modest sum compared to what any meaningful interstellar mission would require, and it could not sustain political support for even a decade. The tunnel for it sits partially dug in Waxahachie, Texas, a monument to what happens to long-duration projects when political cycles end and priorities shift. The International Thermonuclear Experimental Reactor, ITER, the International Fusion Research Project currently under construction in southern France, provides another instructive example. ITER was first proposed in 1985. The international agreement to build it was signed in 2006. Construction began in 2013. The first plasma is not expected into the late 2020s, and the full fusion experiment is not expected until the late 2030s, more than 50 years after the initial proposal and 30 years after the construction agreement. ETR involves 35 nations, represents the most ambitious collaborative scientific project in history, and has a budget of roughly $22 billion. It is a project to demonstrate that fusion energy is scientifically feasible, not to build a power plant, not to build a spacecraft engine, just to demonstrate scientific feasibility. And it has taken half a century to even approach that modest goal. The delays, cost overruns and renegotiations that have accompanied ITER's construction are a preview of what any civilization-scale interstellar project would face, multiplied by orders of magnitude. An interstellar mission requires fusion propulsion, or something more of all these things that we know are entertaining, not just a civilization or a civilization scientist. It requires the engineering of such propulsion into a working spacecraft. It requires the construction of that spacecraft. It requires the political will to launch human beings into a void from which they cannot return, toward a destination that offers no guarantee of anything. The timescale from fusion propulsion demonstrated to interstellar mission launched is not a decade. It is at least a century, probably more. Some argue that interstellar travel will become motivated by necessity, by the overpopulation of Earth, by resource depletion, by the search for new habitable worlds. This argument fails on the physics. Even at 10% of the speed of light, a speed we cannot achieve, the capacity to transport significant numbers of people to another star system is negligible compared to the capacity to simply reduce population growth on Earth, or to expand into the solar system, which is itself vastly more resource-rich and accessible. The asteroid belt alone contains more mineral resources than any conceivable interstellar colony could access for millennia. The other planets and moons of our solar system contain resources beyond any current need. The motivation of necessity, which drives so much of human exploration and migration, does not logically extend to interstellar space when the solar system itself is so much more accessible and resource-rich. A civilization threatened by an existential catastrophe, a dying sun, an impending asteroid strike, a nearby gamma-ray burst, might develop different motivations. But a gamma-ray burst lethal enough to sterilize Earth would arrive at the speed of light, giving no warning time for preparation. An impending asteroid strike is centuries in the future if detected with current technology, and deflection is far more energy efficient than evacuation. The sun's death is 5 billion years away. None of these catastrophes provides a motivation for interstellar travel that is realistically connectable to human decision-making on any accessible timescale. Others argue that interstellar travel will be achieved not by biological humans, but by artificial intelligence, by robotic or digital minds that do not suffer from the biological vulnerabilities of human crews, that do not require food or breathable air, that can operate indefinitely in deep space, and that can sustain a mission for any length of time without the ethical problems of generation ships. This is a more serious argument, and it deserves careful consideration. An artificial intelligence or robotic probe faces none of the biological limitations of a human crew. It does not age. It does not need food or water. It is not susceptible to the psychological deterioration of long-term isolation. It can, in principle, be placed in a low-power maintenance mode during the cruise phase and awakened on arrival. It does not require deceleration. A flyby probe that transmits data during its encounter with the destination system provides exactly the kind of information that makes interstellar exploration worthwhile without the need to slow down. This argument is correct, and it significantly changes the calculus of interstellar travel. For robotic probes, the breakthrough starshot concept, which proposes gram-scale light sails accelerated to 20% of the speed of light by a ground-based laser, is a serious proposal for exactly this kind of mission. At 20% of light speed, the journey to Alpha Centauri takes 21 years. The probe arrives, flies through the system in a matter of hours, and transmits its observations back. Earth receives the signal 4.24 years after the flyby. Total time from launch to data, approximately 25 years. This is, in principle, achievable by a sufficiently advanced version of technology we already understand conceptually. The obstacles are engineering, building a laser array of sufficient power, fabricating a sail of sufficient reflectivity and thermal resistance, designing a gram-scale spacecraft with sufficient instruments and communication capability. But they are engineering obstacles, not fundamental physics obstacles. But this is not interstellar travel, in the sense that the human imagination has always meant by that phrase. It is robotic reconnaissance. It does not put humans at another star. It does not establish a presence, a colony, a civilization at another stellar system. It is the equivalent of sending a camera-equipped ballistic missile to another country. Valuable information is obtained, but no one went there. The human dream of interstellar travel, of going there, of standing on another world under another star, of meeting what or who might be there, of building something lasting in another solar system. This is not achieved by a gram-scale flyby probe, any more than the dream of circumnavigating the globe was achieved by a message in a bottle that washed up on the other side. And here is where the argument becomes genuinely profound, rather than merely technically challenging. The question of whether interstellar travel will happen is not just a question about propulsion systems and life support and navigation algorithms. It is a question about what humanity, or whatever intelligence emerges from humanity, will be and want across the timescales required. Because the honest answer to "can interstellar travel happen" may be different from the answer to "will interstellar travel happen?" And the difference lies in the nature of intelligence and civilization over very long time periods. Consider the following. The technologies that would make interstellar travel even marginally feasible: true fusion power, antimatter production and storage, artificial general intelligence vastly beyond current capability, material science at atomic precision for radiation shielding, closed-loop life support for indefinite duration, are technologies that are themselves transformative in ways that change what intelligence is and what it wants. A civilization that has achieved true fusion power is a civilization with effectively unlimited energy for earthly purposes, and the motivation for high-energy interstellar travel changes when energy is abundant. A civilization that has developed artificial general intelligence has, by definition, developed minds that may have entirely different attitudes toward time and distance than biological human minds. A civilization with indefinite life extension technology is a civilization where the trade-off between the life of an individual and the duration of an interstellar voyage looks completely different. What? The technologies that make interstellar travel possible, in other words, are technologies that simultaneously transform the nature of the civilization that would use them. We cannot reason about whether a civilization with those technologies would choose to make interstellar voyages by extrapolating from the values and motivations of biological humans today, any more than a medieval peasant could reason about what a civilization with computers and nuclear weapons would do with its power. The future that contains interstellar travel, if it exists, also contains minds and motivations that are as different from ours as we are from the earliest hominids. We cannot know what they will want, and therefore we cannot know whether interstellar travel is something they will pursue. The technologies that make interstellar travel possible, in other words, are technologies that simultaneously transform the nature of the civilization that would use them. We cannot reason about whether a civilization with those technologies would choose to make interstellar voyages by extrapolating from the values and motivations of biological humans today, any more than a medieval peasant could reason about what a civilization with computers and nuclear weapons would do with its power. The future that contains interstellar travel, if it exists, also contains minds and motivations that are as different from ours as we are from the earliest hominids. We cannot know what they will want, and therefore we cannot know whether interstellar travel is something they will pursue. This is not a reason to say interstellar travel will never happen. It is a reason to say that the question, will interstellar travel happen, is not answerable from our current position, because it depends on the nature of future intelligence in ways we cannot predict. But there is a separate, more constrained version of the question, which is, will biological humans, people like us, with our biology, our psychology, our values, our institutional structures, ever cross the space between stars? And to this question, the physics gives a more definite answer. Not impossible in principle, but extraordinarily, perhaps prohibitively difficult in practice. It is worth examining the most technically sophisticated proposals for near-term interstellar missions in detail, because doing so illustrates both how much progress has been made in theoretical design and how far the remaining obstacles are from being resolved. Project Daedalus, the British Interplanetary Society's 1970s study of an uncrewed fusion-propelled interstellar probe, remains the most detailed engineering study of any interstellar mission concept. The design involved a two-stage spacecraft, 54,000 tons at launch, propelled by inertial confinement fusion of deuterium-helium-3 pellets detonated at a rate of 250 per second. The calculated final velocity was about 12% of the speed of light, giving a 50-year journey to Barnard's star, about 5.9 light-years away. The design was technically self-consistent within its assumptions. Its problems were the problems of the assumptions. Deuterium-helium-3 fusion has never been achieved in a sustained, controlled fashion in any laboratory on Earth. Helium-3 in the quantities required, about 30,000 tons, does not exist in any accessible form. It would need to be mined from the atmospheres of the outer planets. The 54,000-ton launch mass exceeds the total mass of everything humanity has ever launched into space by a factor of roughly 10,000, and Daedalus was designed as an uncrewed mission. The crew version of such a mission would be orders of magnitude more massive. Project Icarus, a follow-on study conducted in the 2150s by a group of volunteers at the British Interplanetary Society, attempted to update and improve on Daedalus with contemporary physics and engineering knowledge. The study ran for several years and produced detailed analysis of propulsion, structure, navigation, communication, and science payload. Its conclusions confirmed and deepened the challenges identified by Daedalus. Fusion propulsion is physically plausible for interstellar missions, but requires technologies, controlled fusion ignition, large-scale helium-3 mining, precision high-rate pellet injection, that are all individually decades away from demonstration, and whose simultaneous development would require a sustained, coordinated engineering effort comparable to the Manhattan Project, but lasting for generations. The Breakthrough Starshot initiative, announced by Yuri Milner and Stephen Hawking in 2016, represents the most serious contemporary effort to think rigorously about an actual interstellar mission. The proposal, a gram-scale light sail, driven by a 100-gigawatt ground-based laser array, accelerated to 20% of the speed of light in a few minutes, reaching Alpha Centauri in 21 years. The technical challenges identified by the Starshot team are numerous. The sail must be 100,000 times more reflective than current sail materials to survive the laser intensity without vaporizing. The laser array, 100 gigawatts focused on a target a few meters across, would be the most powerful directed energy device ever built by a factor of millions, and its construction would require new generations of high-power laser technology. The sail must maintain precise orientation under the beam pressure, with attitude control systems that do not yet exist. The gram-scale spacecraft must contain instruments, power systems, and a communication laser powerful enough to transmit data across 4.24 light-years, a task that challenges current communication technology even at Earth-Mars distances. The sail must survive the interstellar dust bombardment described earlier, which at 20% of the speed of light is even more severe than at 10%. None of these problems has been solved, even in principle. Progress is being made. New metamaterials with high reflectivity are being studied. Laser array phasing techniques are being explored. Miniaturized communication systems are being developed. But the gap between current technology and the requirements for even a gram-scale flyby probe is still measured in orders of magnitude in several independent parameters simultaneously. The project's own team, which is among the most technically sophisticated groups thinking seriously about interstellar travel, does not claim that Starshot is imminent. They describe it as a decades-long research and development program whose success is uncertain. All of these considerations, the energy problem, the time problem, the engineering problem, the deceleration problem, the radiation problem, the motivation problem, combine to produce a picture that is different from the one presented in popular culture, which treats interstellar travel as inevitable, as the natural next chapter in humanity's exploratory story, as something that is merely a matter of time and will. The honest picture is more nuanced. Let us examine the most technically sophisticated concrete proposals for interstellar missions, because doing so illustrates both how much progress has been made in theoretical design and how deep the remaining gaps actually are. Project Daedalus, the British Interplanetary Society's 1970s engineering study of an uncrewed fusion-propelled interstellar probe, remains the most detailed and technically rigorous interstellar mission concept ever produced. The design involved a two-stage spacecraft, 54,000 tons at launch, propelled by inertial confinement fusion of deuterium helium-3 pellets, detonated at a rate of 250 per second, at the base of a large magnetic field pusher plate. The calculated final velocity was about 12% of the speed of light, fast enough for a 50-year journey to Barnard's star, 5.9 light-years away. The mission would be uncrewed, flyby only, transmitting data back to Earth during the brief hours when it passed through the target system. The design was technically self-consistent within its assumptions, and the team behind it was serious. including engineers and physicists who worked through the systems in extraordinary detail over several years. But the assumptions are where the problems hide. Deuterium-helium-3 fusion, the primary reaction proposed for Daedalus, has never been achieved in a sustained, controlled fashion anywhere on Earth. The inertial confinement fusion ignition, achieved at the National Ignition Facility at Lawrence Livermore in December 2022, was a landmark event, the first time a fusion reaction produced more energy than was delivered to the target, but it used a different reaction, deuterium-tritium, and the scale is daunting. The NIF facility is the size of a football stadium. It compresses one tiny pellet at enormous cost and complexity, and it fired its ignition pulse once per campaign. The Daedalus requires firing hundreds of pellets per second, continuously, for years. The gap between a demonstration and an engineering system is measured in multiple orders of magnitude in power, repetition rate, and efficiency. The National Ignition Facility's deuterium-tritium experiment is not a prototype for Daedalus. It is a proof of concept for the relevant physics, separated from Daedalus by engineering challenges that would take generations to bridge. The helium-3 fuel requirement, 30,000 tons of helium-3, compounds the problem. Helium-3 is extraordinarily rare on Earth, present only in trace amounts from radioactive decay and solar wind absorption. The Moon's surface contains some helium-3 in quantities potentially useful for fusion reactors on a multi-decade scale, implanted by the solar wind over billions of years. The outer planet atmospheres, particularly Uranus and Neptune, contain far more, but mining helium-3 from a gas giant's atmosphere is a concept that has no engineering precedent, even in principle. The 54,000-ton launch mass alone exceeds the total mass of everything humanity has ever launched into space, including every rocket, every satellite, every spacecraft, every astronaut spacesuit, combined by a factor of 10,000. Project Icarus, the follow-on study conducted by the British Interplanetary Society in the 2150s and 2010s, brought contemporary physics knowledge to bear on the Daedalus framework and arrived at conclusions that were, if anything, more sobering. The Icarus team explored fusion antimatter hybrid concepts, pulsed fission fusion engines, and other approaches, and confronted the deceleration problem that Daedalus had avoided by going for a flyby. The team's most promising deceleration concept was the magnetic sail, a large superconducting loop deployed ahead of the spacecraft that creates drag against the magnetic field and charged particles of the target star's stellar wind. The physics is plausible. The engineering is formidable. The loop must be hundreds of kilometers in diameter, must be superconducting at the temperatures of interstellar space, must be deployed without tangling from a spacecraft traveling at 12% of light speed, and must survive the mechanical and electromagnetic stresses of decelerating a 10,000-ton spacecraft from 12% of light speed to orbital velocity. No material we currently have makes a superconducting loop of this size and mass that is simultaneously strong enough to withstand the deployment forces and light enough to carry. The Icarus team identified this as a major unsolved problem and proposed further research that has not yet been done. The Breakthrough Starshot initiative, announced in 2016 with significant backing from Yuri Milner and the participation of Stephen Hawking, represents the most serious contemporary public commitment to working toward actual interstellar flight. Starshot focuses on the lightest possible probe, gram-scale, uncrewed, flyby only, driven by a ground-based laser array to 20% of the speed of light. The appeal is the gram scale. At a gram, the energy required is manageable, the mass ratio problem is muted, and the entire concept avoids the rocket equation by using external propulsion. At 20% of light speed, Alpha Centauri is a 21-year journey. The probe arrives, sweeps through the system, transmits data, and recedes. Earth receives the signal 25 years after launch. The Starshot team has been admirably transparent about the technical challenges. The laser array, 100 gigawatts of coherent laser power focused on a square meter sail, would require phase-locking tens of thousands of individual laser rotors across a square kilometer ground array with sub-wavelength precision, maintained continuously during the minutes of acceleration. Nothing remotely approaching this has been built. The sail material must be simultaneously extremely thin to minimize mass, extremely reflective to maximize thrust and avoid vaporizing, structurally stable under the enormous photon pressure, and thermally robust enough to survive the intense heating from the 0.1% of laser light it absorbs. Current sail materials are not within orders of magnitude of this specification. The grand-scale spacecraft must somehow contain a camera, a communication laser, power generation, attitude control, and whatever instruments are needed to characterize the Alpha Centauri system, while fitting in a few centimeters and massing about 1 gram. The communication laser on board must be powerful enough to transmit data across 4.24 light-years to a receiver on Earth, a receiver that might itself be a large telescope. And the data rate achievable from 4.24 light-years with a gram-scale transmitter is pitifully small. Estimates suggest perhaps a few bits per second at best, enough to know the probe arrived, but barely enough for a single low-resolution image per day. None of these is an impossible problem in isolation. Each one is a decades-long research program. Together, they represent a technical development agenda that the Starshot team itself describes as requiring 20 to 30 years of basic research before mission design can seriously begin, with an actual mission launch perhaps 50 to 100 years in the future. And that timeline assumes sustained funding, no catastrophic failures, and solutions to all the technical challenges that had not yet even been posed in their full detail. This is the state-of-the-art, the most serious, best-funded, best-staffed current effort toward interstellar flight aims at a gram-scale flyby probe that might launch in 50 to 100 years, assuming everything goes well. Not a crewed mission. Not a rendezvous. A 1-gram camera that sweeps through the nearest star system at 20% of light speed and sends back a few blurry pixels a day. This is not dismissible. It would be a genuine scientific triumph and a landmark achievement of human engineering, but it is also the maximum of what serious physicists and engineers think is achievable within the lifetime of anyone alive today. The gap between this and the interstellar travel of science fiction, crewed ships, destinations of choice, two-way communication, galactic civilization, is not a gap that the next few generations of technology will close. Having surveyed this landscape, we arrive at the question that I promised at the outset deserves the most philosophical attention. And the question connects the obstacles we have described to one of the deepest puzzles in modern science, the Fermi paradox. In 1950, over lunch at Los Alamos, the physicist Enrico Fermi made a calculation that has troubled astronomers and philosophers ever since. The galaxy is about 13.5 billion years old. Even at a tiny fraction of the speed of light, at 0.1% or 300 kilometers per second, which is achievable with advanced nuclear propulsion, a self-replicating probe could colonize the entire Milky Way in about 100 million years. If any civilization in the galaxy developed such probes even 5 billion years ago, The galaxy should be visibly colonized right now, and yet it is not. No alien megastructures, no directed signals, no von Neumann probes in our solar system. No evidence of any civilization anywhere in the galaxy. The sky is silent. A von Neumann probe, a self-replicating machine that travels to a new stellar system, uses local resources to build copies of itself and sends those copies onward, is the most energy-efficient imaginable approach to galactic exploration. It solves the motivation problem by being autonomous. It solves the resource problem by using local materials. It solves the timescale problem by propagating exponentially. A single probe launched by any civilization, anywhere in the galaxy, at any time in the past 5 billion years, would have reached every stellar system in the galaxy by now. If such probes were ever sent, they would be here. They are not here. Why? The solutions to the Fermi paradox divide into roughly 3 categories. Life is rare. The origin of intelligence is so improbable that we may be genuinely alone. Civilizations are self-destructive. Every civilization that reaches technological maturity destroys itself before developing interstellar capability. Or, the physics of interstellar travel is simply too constraining for any civilization to implement, and the galaxy has never been colonized because no civilization has ever found a way to cross the distances. This last option, the physics is filter hypothesis, has received less attention than the others, but aligns precisely with the engineering analysis we have been conducting. If the rocket equation, the speed of light, the energy requirements of relativistic travel, and the interstellar medium radiation environment are as constraining for every civilization as they are for us, if these are universal physics, which they are, then the Fermi paradox dissolves. There is no paradox. Every civilization, everywhere in the galaxy, reaches the same conclusions we have reached. The distances are too great. The energy is too much. The time is too long. The engineering too far. And so, the galaxy is quiet, not because civilizations are rare or destructive, but because the universe is structured in a way that keeps intelligence local, that makes every solar system a sealed system in all but the deepest, most geological timescales. The silence is not a mystery. It is physics. But the honest picture also demands honesty about what we do not know. Our understanding of physics is extraordinary, but not complete. General relativity and quantum mechanics are the 2 pillars of the physical description of the universe, and they're incompatible at the Planck scale, the regime of the smallest distances and the highest energies. The theory of quantum gravity that must eventually reconcile them does not yet exist in completed form. String theory, loop quantum gravity, and other approaches have illuminated aspects of the problem, but not solved it. It is not impossible, it is not even particularly unlikely, on historical grounds, that a completed theory of quantum gravity will reveal new phenomena, new possibilities, new physical processes at very high energies that are not contained in our current physics. The history of physics is a history of revolutions. Newtonian mechanics, electromagnetism, thermodynamics, special and general relativity, quantum mechanics. Each one revealed phenomena not visible at lower energies or smaller scales. And each one opened possibilities that were literally inconceivable before it. It would be extraordinarily arrogant to claim that our current physics is the final physics, that there are no more revolutions, that the universe has no more surprises. This caveat matters enormously, and it deserves full consideration rather than dismissal. The 2 most frequently discussed exotic proposals for circumventing the speed of light barrier, wormholes and Alcubierre warp drives both exist within the framework of general relativity. They are not science fiction in the sense of being invented for narrative convenience. They are solutions to Einstein's field equations, which are the governing equations of space-time geometry, as rigorously verified as any equations in physics. A wormhole, sometimes called an Einstein-Rosen bridge, after the paper Einstein and Nathan Rosen wrote in 1935 describing the concept, is a topological feature of space-time in which two distant regions are connected by a short tunnel through the geometry of the universe. The analogy is a sheet of paper. If you want to travel from one side of the sheet to the other, you can either walk across the surface, a journey of the paper's full width, or you can fold the paper so the 2 points are adjacent and poke a hole through both, creating a direct connection that bypasses the surface entirely. A wormhole is the hole in the folded paper, and the folding is a deformation of space-time geometry caused by the distribution of mass and energy. The mathematics of transervable wormholes, ones that a spacecraft could actually pass through without being crushed, was worked out in 1988 by Kip Thorne and Michael Morris, and subsequently refined by many researchers. The critical requirement for a transervable wormhole is a region of negative energy density at the throat of the wormhole, a region where the energy of the vacuum is less than zero. This is needed to hold the wormhole open against the gravitational tendency for such a structure to collapse. Negative energy density is not entirely outside the framework of quantum mechanics. The Casimir effect, first predicted by Hendrik Casimir in 1948 and experimentally confirmed in 1997, demonstrates that the vacuum between two closely spaced metal plates has a lower energy density than the vacuum outside, a measurable, laboratory-confirmed instance of negative energy density. But the magnitude of the Casimir effect is tiny. It requires plate separations of nanometers and produces force densities useful for precision measurement, but nowhere near what a macroscopic wormhole throat would need. The amount of exotic matter with negative energy density required to hold open a traversable wormhole of spacecraft size, based on calculations by Thorne, Morris, and subsequent researchers, is staggering. Estimates vary with the wormhole geometry and the required transit conditions, but they consistently come out as negative energy, equivalent to the mass energy of a planet or star, with a negative sign. Not micrograms, not kilograms. Planetary or stellar masses of exotic matter with negative energy density. Quantum field theory places constraints on how much negative energy can exist in any finite region of space, the so-called quantum inequalities, derived by researchers including Larry Ford and Tom Roman, and these constraints are very restrictive. They do not obviously make macroscopic traversable wormholes impossible in principle, but they make them extraordinarily difficult to reconcile with any realistic physical process we know of. The gap between the Casimir effect, picojoules of negative energy in a laboratory, and the requirements for a traversable wormhole, negative planetary mass energy, is, if anything, larger than the gap between current antimatter production and the needs of an antimatter rocket. The Alcubierre warp drive, proposed by Miguel Alcubierre in 1994, is a different kind of exotic geometry. Alcubierre's insight was that special relativity prohibits objects from moving through space faster than light, but says nothing about space itself moving. The expansion of the universe carries distant galaxies away from us at speeds exceeding light, not because the galaxies are moving through space, but because the space between us is expanding. Alcubierre proposed creating a bubble of space-time around a spacecraft, in which space in front of the bubble contracts, and space behind it expands, effectively carrying the spacecraft along, like a surfer on a wave. The spacecraft inside the bubble is locally at rest. It feels no acceleration, no tidal forces, experiences no violation of special relativity in its immediate vicinity. But the bubble itself can be moved at any speed, because the space-time is moving, not the spacecraft. The mathematics work out cleanly. The metric Alcubierre proposed is a valid solution to the Einstein field equations, and it allows, in principle, faster-than-light effective travel with no local special relativistic violation. The physical problems are severe, but interesting. Like traversable wormholes, the Alcubierre drive requires exotic matter, in this case, a region of negative energy density in the wall of the warp bubble, with total negative energy comparable to the mass of the planet Jupiter. Harold White at NASA spent several years investigating whether different bubble geometries, thinner bubble walls, oscillating metrics, could reduce the negative energy requirements. And his calculations suggested they could, in principle, reduce the requirement by many orders of magnitude. These calculations were controversial and have been disputed, but they motivated some laboratory experimental work at NASA's EagleWorks laboratory, attempting to detect small space-time metric perturbations using laser interferometry. The EagleWorks experiments found, tentatively and with significant uncertainty, some anomalous thrust readings in an electromagnetic drive concept that some researchers interpreted as potentially consistent with a metric effect. The results were not reproducible by other groups and are now generally considered to have been measurement artifacts rather than a real effect. But the episode illustrates both the seriousness with which some physicists take the warp-dive concept and the extraordinary difficulty of testing it empirically with current technology. Beyond the exotic matter requirement, Alcubierre and other researchers identified additional problems with the warp drive that are independent of the energy question. The spacecraft inside the warp bubble is causally disconnected from the bubble wall. Light signals from inside the bubble cannot reach the front wall fast enough to control it or turn it off. Any astronaut inside could not, in principle, steer the warp drive or stop it using any mechanism that operates at or below the speed of light. The warp drive, once activated and running faster than light, is a runaway process from the perspective of the occupants. This is a fundamental problem of causality, not merely of engineering design. Additionally, Stephen Hawking and others identified that the quantum vacuum in the presence of a warp bubble would be destabilized by high-energy particle creation at the bubble wall, analogous to Hawking radiation at a black hole event horizon, potentially destroying the warp structure from within. These are theoretical problems, and theories can be wrong, but they represent serious obstacles within the framework of our current best physics. What is the honest conclusion about wormholes and warp drives? They're not ruled out by general relativity, they appear in its mathematics. They're not ruled out by any observation. No observation has ever tested the exotic matter requirements at the relevant scales. But they require physics, specifically the ability to engineer negative energy density at macroscopic scales that is not supported by any currently known physical mechanism, and that may be fundamentally constrained by quantum mechanical inequalities that we do not yet know how to circumvent. They are possibilities in the mathematical sense. Whether they are possibilities in the physical sense depends on quantum gravity, on the as yet unwritten theory that reconciles general relativity and quantum mechanics at the Planck scale. Until we have that theory, And until that theory tells us whether macroscopic negative energy density is achievable, the status of wormholes and warp drives remains genuinely uncertain, neither confirmed possible nor confirmed impossible. This is intellectually honest, but practically inconclusive. For planning purposes, for thinking about whether interstellar travel will happen in any time frame relevant to human civilization as currently constituted, the honest position is that wormholes and warp drives are speculative technologies dependent on physics we do not have, while the obstacles to conventional interstellar travel are enormous and based on physics we are confident about. The probability that the speculative technologies resolve the obstacles in any time frame shorter than the geological timescales that conventional interstellar travel requires is unknown, but not obviously high. The honest position, therefore, is not interstellar travel will never happen, but something more precise and more intellectually honest. Interstellar travel, as currently imagined, and with currently known physics, faces obstacles that may be permanently insurmountable for biological humans, and may be achievable only with either transformative technological developments over very long timescales, or with new physics currently unknown to us. That is not never, but it is much, much harder than popular culture suggests, and the probability that it happens within any timescale that matters to people currently alive is very close to zero. There is also a philosophical dimension to the question that is worth examining honestly, because it changes the emotional register of the discussion. Much of the motivation behind the human dream of interstellar travel is the implicit assumption that the stars hold something we need: other civilizations, other habitable worlds, a destiny that extends beyond a single solar system. But consider this: if the physics of interstellar travel is as difficult as we have described, and if the same physics applies everywhere in the universe, then other civilizations, if they exist, face the same obstacles. The Fermi paradox, the absence of any detectable evidence of other civilizations despite the age and size of the galaxy, may have a simple explanation. The distances between stars are simply too large for any physically realizable civilization to bridge on timescales shorter than geological epochs, and the galaxies therefore not colonized. Not because civilizations are rare, hang nobody for the time will be affected, but because the physics of the situation. Every civilization, everywhere in the galaxy, sits in its own solar system, looking out at the stars, doing the physics, reaching the same conclusion: the distances are too great, the energy requirements too extreme, the time too long. In this reading, the silence of the universe is not a tragedy. It is not a sign that we are alone, or that civilizations destroy themselves before reaching the stars. It is a sign that the universe is structured in a way that keeps civilizations in their home systems, not as prisoners, but as inhabitants of a domain that is, for any technology we can reasonably envision, effectively infinite within itself. The solar system alone contains more matter, more energy, more volume, more potential for the development of intelligence and civilization than any single civilization could exhaust in billions of years. The asteroid belt, the outer planet moons, the Oort cloud, the Kuiper belt, these contain resources and environments that we have barely begun to catalogue, let alone explore. The solar system is not a waiting room. It is a civilization's entire world, and a sufficient one for billions of years of development. This perspective that interstellar travel may be effectively impossible for any civilization at any technology level, and that this is simply a feature of the universe's architecture rather than a temporary engineering challenge, leads to a different kind of realism about our place in the cosmos. We are not the larval stage of a galaxy-spanning civilization growing through our technological childhood toward a glorious interstellar adulthood. We may be, and the physics suggests we probably are, permanently local, permanently bound to this solar system, to this star, to this particular corner of the Milky Way. Not because we lack ambition or ingenuity, but because the universe is very large and very empty, and the speed of light is very finite, and the energy required to bridge the void is very enormous. That is not a comfortable conclusion for a species that has always defined itself partly through exploration, through the desire to see what is over the next horizon. But comfort is not the standard by which physics is judged. The standard is accuracy. And the accurate picture of interstellar travel is extraordinarily difficult, possibly prohibitive for biological life, potentially achievable over very long timescales with very advanced technology. Dependent on new physics for the scenarios that most capture the imagination, and likely delayed, if it ever happens at all, by timescales that are geological rather than historical. There is, however, a different way to read this conclusion, not as confinement, but as an invitation. If we are permanent inhabitants of this solar system, not travellers through the galaxy, then the appropriate response is not frustration at our limitations, but engagement with the extraordinary richness of what we have. The solar system contains 8 planets, hundreds of moons, millions of asteroids, billions of comets, a diversity of worlds and environments, and resources that dwarfs the total of what any interstellar civilization could realistically explore in comparable timescales. The Earth itself, with its oceans and atmospheres and biosphere, with the 8 billion humans and trillions of other organisms that call it home, is more complex, more interesting, more worthy of exploration and understanding than any single exoplanet we will ever observe, even with our best telescopes. The universe beyond the heliopause is real and extraordinary and worth knowing about. But the universe within reach of our lives and our civilization is not a consolation prize. The stars are beautiful precisely because they are unreachable. Not unreachable because we haven't tried hard enough, not unreachable because we haven't been clever enough, but unreachable in the way that the past is unreachable, because the structure of the universe, in its depth, in its scale, and its speed of light limit, makes them a different kind of thing from the worlds we can visit. They are the frame of our picture, not the subject. The subject is here, in the solar system that made us, in the planet that shaped every cell in our bodies, and a civilization that has spent 10,000 years learning to understand the universe from a single, specific, irreplaceable vantage point. Perhaps that is enough. Perhaps it is more than enough. Perhaps the right response to the discovery that interstellar travel may never happen is not disappointment, but something rarer, a genuine, unflinching appreciation of the place where we already are, this small, wet, spinning, electromagnetically noisy planet, orbiting an ordinary star in the outer suburbs of an average galaxy, containing within its iosphere and its civilization a complexity and a wonder that the empty, silent, cold spaces between the stars will never, in all probability, come close to matching. The stars are out there, the distances are real, the physics is what it is, and we are here, and here is where everything that has ever mattered has happened, and where everything that ever will matter for us and for whatever we become will happen next. That is not a small thing. That is, by any measure, everything.